connection is similar. But with the union, and I say it's similar because it's somewhat different. It says assume you have sets U alpha that I O, but not just U1 and U2 because U and D, but this alpha can come from an arbitrary index set. So here, if you wish, I chose index set 1 and 2, I have two sets. But this index set could be the real line. It could be more than countably many elements. It's a huge collection of elements in this O. However, whatever amount of subsets in O you look at, the union, the big union over all of the ones you already have in O, this big union, these brackets are not necessary that make the thing clearer, this big union also needs to be in O. If that is not the case, then the whole thing is not called a topology. That's it. This is the key definition of topology. And of course the question is, what is this all about? Another question is, can we have an example? Example, let's start very simply. Let's say that M is just consists of elements 1, 2, 3. We need to understand this before we understand it. Now, we could, for instance, make a joint of subsets. So I make a big bracket, okay, big bracket, and this all contains subsets of M. For instance, it could contain the empty set. And it could contain the sets 1, 2, 3 itself, and these are the only subsets of M. This all is called O1, which contains. The question is this a topology? If it is a topology, it's going to go through it. The empty set lies in it. The entire set, 1, 2, 3, lies in it. We take two arbitrary sets and check whether the intersection lies in them. I choose this one as U, and I choose the same one as me. Why not? MC intersects with MC is MC, MC is already in there. I take this one, MC intersected with this one, MC intersected with anything, this MC, MC is already in there. I take this one with that one, well, the intersection is symmetric, again MC, MC is already in there. I take this one intersected with itself, it's 1, 2, 3 again, it's already in there. Second action satisfied. Third action for the union, the same holds true. The only finite union is the topology here. No, in fact it won't, because for instance, if N is the integers, N, then the power set of N is isomorphic to the real. So in the topology, we can choose O as the entire power set. That would be the next example. So to answer your question, does the topology have to be countable? The answer is no, even if M is countable. Okay, next example, B, same set up here, so A should go here. O2 is defined as the empty set, the set 1, the set 2, and the set 1, 2, 3. Is this a topology? The answer is no, because 1, union 2, so actually we need to check 1 union 2 is set 1, 2, is not in there, it's not a topology. Okay? Now, this is a very simple game if you're able to write down the topology explicitly. Now, the two topologies you can establish on any set. So let's do example 1, example 2, any set. So for instance, the set of integers, all the real numbers, whatnot. We have the following example. You can choose the topology to be to consist of only the empty set and the entire set. And this is a topology that has a specific name. It's called chaotic topology. You can check this is a topology for any set N. There's a second topology that you can always write down, and that's the topology where you just take any subset of the chosen set, just any one, and because of the intersection of the subset is always a subset, and the union of the subset is always a subset, and all the subsets are in there, this also is a topology, and it's called a discrete topology. Why should we worry about the chaotic and the discrete topology? The answer is because they're both utterly useless. They're utterly useless, but the extreme cases. The extreme cases because this is the topology with the fewest elements possible, and this is the topology with the maximum amount of elements possible, and they serve as test cases in order to construct extreme examples of topology in order to have an understanding of what the most has. Not topology, since the union of 1 and 2 is the element is the set 1, 2, and this 1, 2, 3. And the set 1, 2 is not an element of the set, because this is an element of the set, this is an element, this is an element, and this is an element. Okay? Yes, exactly. Okay, so the other really useless, but they serve as good examples. Now, there is a very important example that we're going to use throughout, and that will reconcile your intuition that you of course have from undergraduate analysis of continuity, which we're going to define soon, with the notion of topology, and that is the so-called standard topology. But whereas the chaotic and discrete topology, these two utterly useless ones, can be defined on any set, the ones I'm going to define now can only be defined on RD. What is RD? RD is R cross dot dot cross R. And what is that? That's the set of all the Z tuples of real numbers, so Ti are in real numbers. So in RD lie tuples of G numbers. Okay, that's RD and that's the set. And now on this set, we want to establish a topology. We could establish a chaotic topology, we could establish a discrete topology, we could establish a great number of different topologies. We are now going to establish the topology that is usually chosen without saying it. Okay? That's the point. And this is called the standard topology. So we want to define O standard. So this needs to be a subset of all the subsets of the power set of RG, of course, because it's a topology. And you see here, I explicitly wrote down all the elements that belong to the topology. The same here, I explicitly wrote it down. Now, the standard topology will contain non-countably many elements. I can impossibly write them down explicitly. I have to define this implicitly and then to check whether this nevertheless you need to define the topology, okay? So the way of definition is somewhat different, but the idea is of course the same. And the definition proceeds in two steps. The first step is to define the so-called softball. What is a softball? The softball is a set D, R sub R of a point T. So the point T is supposed to be in RD, and R is supposed to be an element of the positive reals. Well, this is going to be the radius of the ball, and this is going to be the center of the ball, if you like to think about it like this. And in fact, it's just a set, meaning it's all the Q1, QD, right, the D tuple, the element of RD, for which it is true, now it comes, that if you take the ith member of this point in RD, you subtract from it the ith member of the central point. So this is the point T in RD that it has components P1 to PD, okay? You square the differences, you go from I equals 1 to D, and you require that the whole thing is less than R squared. And of course you see, oh, what you're writing down here is just the Euclidean norm, is what you say. And I didn't speak of a norm, and I don't need to speak of a norm, and this is actually just defined on tuples. I do not need a vector space structure on RD to write this down. To write down a norm you do. Anyway, this is the softball, and there's of course a softball for any R and any P. So that's step number alpha. Now step number beta is the following. We declare that the set U be in the topology that we call the standard topology. By definition, if and only if, the definition, the implicit definition, if the following is true. If for every point P of the set in question, there exists an R in R plus, such that the softball GR of T lies entirely in the set U. This is the definition, and of course, you can just think of this in a very simple way. So this is thinking, and the other thing is mathematics. You can think of it in the following way. Assume you're looking at R2, this special case, and you think this is part of R2 in your intuition. And now I take this set here, where the boundary does not belong to the set, roughly speaking. And now the question, is it true that this set U, is it an element of the standard topology? Well, yes it is. Because whatever point in U you pick, you find a intuition radius small enough such that the softball, because there is not an equal sign, right, whose softball lies entirely in there. That's true for every point. Whereas if you have taken only some part of the boundary here to still belong to the set, you could have chosen a point on there, right, for any point must be true, but then however small but positive you choose the radius, you would always have a problem here because the ball wouldn't lie fully in it. So this new set U is not an element of the topology, whereas before the set was. And now it's a simple exercise, but for reasons of time I'm not going to give it. It's a simple exercise you might think about why it is true that the thus implicitly defined topology satisfies these three axioms. Okay? Maybe you want to think about this tonight. Okay? So very simple, it's a few lines proof. Can I have the possibility? It's a few lines proof, but we'll leave it out. But of course, these pictures you saw before, and you would have probably said this is an open set and this is a non-open set and so on. And this is precisely the reason for defining this special topology this way, to do on RD what you always knew. But it doesn't mean that there wouldn't be opportunities to maybe equip RD with a different topology if you have the other than the standard purposes in mind. And later on, what we're of course going to do, we're going to think of M, the set as the points of space-time, then one big question will be, what topology should the physical space-time, or rather our mathematical model, carry? There is a huge choice of topologies. Anything that fits into this scheme is a topology. Anything that fits into the scheme, as we will define now, suffices to define continuity of maps. Remember, we define topologies in order to be able to define continuity of maps. Okay. So this will be the next step, but before I go there, please do not be deterred if this is abstract at first sight. I don't know what your background, if you're a mathematician, you'll say, well, this is just how things go. If you're a physicist, you sometimes have to think about in what places you usually implicitly make these assumptions, and one of the tasks in order to understand space-time is to make the implicit assumptions explicit. In fact, when Einstein wrote down general relativity, he didn't understand many of the implicit assumptions, and it took him many, many years to overcome intuitive notions, some might say obvious notions, that nevertheless do not apply. So making things explicit allows you to really understand the concepts. And you need to trust me that none of the mathematical notions I introduce is not necessary in order to understand the physics. So really every single bit, later on when we proceed further in the course, I will be able to point at the notions and say, this is the physical effect of this and that choice. Okay? And it was actually, I think, in the second half of the 20th century that Wald, Ehlers, and so on, they recognized general relativity, the theory of space-time, gravity, and matter, must be studied on the differential geometry side at the level of rigor that mathematicians study differential geometry in order to really come to terms with the subtle notions of physics there. Okay? So you need to trust us that this is the cleanest way to introduce it, and everything is self-contained. Okay, so these are my words of motivation here. So now we define a topology. We saw a topology is something you need to choose. It's not automatically there. It's a choice. Whenever you make a choice, it's providing structure. So we have the following important terminology. And this is not only terminology. It's not definition. It's terminology. So we talked about M being a set. In fact, you can make it a problem. What on earth do you mean by a set? A collection of elements? Great. But what's an element and what's a collection? It's not so simple. You need to actually write down axioms for set theory. We're not going to do this. I leave you with the intuitive notions. If in doubt, you do the Melo-Frankel set theory with the axiom of choice. Don't worry. O, we call this a topology, and this is a set of subsets of M with certain properties. Now, if you think of a set together with a choice of topology, you think of this pair. I think them together, and then this pair is called the topological space. It's more than a set. It's a set with additional information. Okay, that's a topological space. Now, if U is an element of O, if U is a subset of M that lies in some chosen topology, which I call O, then we call U an open set. This is just topology, terminology, topology 2. It's a subset of M that happens to lie in the chosen topology is called an open set. So the topology is the set of open sets. But it's not like you would know what open is and then you have the topology. It's rather that open is defined by having chosen a topology. Okay? That's an open set. Then there is another type of set, let's call it A, or it's just a set. Let's call it set A, which is a subset of M, which is a subset of M. Call the set A closed. Call it a closed set. When do we call it a closed set? We call it a closed set by definition if the complement of A, if you take out A from the total space, if the complement lies in the topology. And at this point, you think, closed is the opposite of open in some way. No, not in any way. There are open sets that are closed at the same time. For instance, the empty set. Because the empty set is in O, but M without the empty set is all of M is also in O. So the empty set is also closed. So the empty set is open and closed at the same time, for instance. There are sets that are open but not closed. There are sets that are not open but closed. And there are sets that are not open and not closed. Or in plain English, these two notions, in principle, a priori, have nothing to do with each other whatsoever. Of course, if you have chosen a topology, they're connected by this definition. Okay, so I put up a warning sign. I will do this several times during this lecture. And the warning sign is that from open, it just generally not follow that the set is closed, neither the other way around, despite the deceptive terminology. So I can't think why the empty set is not in my mouth. Depends on what you look at. For instance, if you're a vacuum physicist, in many cases you find examples where this is useful. Okay. And nevertheless, it belongs to the whole picture. You cannot understand the other bits if you don't understand the extreme cases. That's the point. Okay. So now we got ourselves a topology. We got ourselves a number of notions we usually talk about. But now, why did we afford to buy a topology in our favorite topology shop? Okay. The point is, it does as a service. It yields the notion of continuous match. Second, continuous match. Okay. Now, first of all, we need to talk about a map. And you all know what a map is. A map is something that we call S, for instance, and it goes from one set into another set. So N is a set, N is a set, and this set we of course call the domain, and this set we call the target set. And a map is of course nothing but if I picture the set M by the collection of its elements, and I picture the set N by the collection of its elements, then a map, you know it, takes every point from the domain to some point over there. For instance, these 2 points can be taken to the same point, not a problem. We call the map F. This point can be taken here, that point can be taken there, but there is no need that every point is hit. For instance, this point is not hit. Okay? And this point here is being hit twice. We have notions for that. If such diamond point exists, we say the map F. The map F is not surjective, because there's certain not surjective, because certain points in the target are not hit. If there exist points like the flower point, then we say the map is not injective, because some points in the target set are hit more than once. You know these notions: injective maps, surjective maps, and maps. And a map is only defined between 2 sets. You need no further structure on the set in order to say what a map is, right? And not in order to say what injective or surjective is. If it is injective and surjective, it's called bijective and so on. However, I give you this map and ask you a simple question: is this map continuous? Does it make jumps? Now, you may have an intuition of whether it does or not, and the answer is it depends. So what does it depend on whether this map is continuous? Well, in fact, so the answer to the question of whether a map S from N to N is continuous depends, and it does so by definition, so not by some divine intervention, but because we're going to define continuity like this, depends by definition on what topologies are chosen, which topologies are chosen on the domain M and the target space N. In order to decide continuity of a map, you need to decide on some topology here, you say that's the one I want here, and on the topology there, and only then can you write down meaning.